All right. Our last talk of the morning is by Hannah Leung on formally verified Path ORAM in Coq.
All right. Good afternoon, everyone. Thank you all so much for coming here for this talk. I'm Hannah, and very excited to share our work towards formally verified Path ORAM in Coq. And this is joint work with two of my amazing advisors, Dr. Talia and Dr. Chris Fletcher at UIUC. All right, here's the outline of my talk. I don't know if anyone has heard of, probably many of you has heard of Path ORAM, but I'm going to give an overview of it and about the definition, construction, algorithm too, and then show what properties we care about this crypto primitive, namely functional progress and the security property of it. Then we'll move on with approaches, challenges, and then final takeaway. All right, before I move on to the definition, I would like to start with the question, how do we actually preserve user privacy and do secure computation over a remote server? All right. So here's a client server model. Imagine that user would like to do some computation over a cloud service. And there's a powerful attacker present. And the first intuition is to do encryption, right? So you encrypt your plain data and with some key, a private key, and store it in the remote server. Then you can do secure computations like homomorphic encryption, and you do the function directly applied to the ciphertext, or there's secure multi-party computation. And then afterwards, you decrypt it, ciphertext with the key and get your data back. But wait a second, is that all to preserve user privacy? Let's take a closer at our powerful attacker. So what is it capable of? It first can view all contents of memory. And in the remote system, maybe some of the region of memory are encrypted, but while others remain public. All of the addresses are visible to the attacker, and the attacker can also view the memory access patterns. What do we mean by this? It's actually a sequence of read and writes to the remote server with data if you're writing to it. So here, really, we can use encryption to protect the data, but what about addresses? What about addresses when they are secrets themselves? Here's an example where you're indexing an array with a secret index. For example, with the Amazon S3 services, the remote file access, in this case, you're indexing the file system array and your location is sensitive. So the Amazon S3 engineers backends could view all the behaviors of the server, and location of the files could be sensitive. So here, I would like to give you a bit of intuition by observation why memory access patterns can leak information. So here's a heat map of the Linux kernel, and for each of the memory address, the darker it is, like you can see some of the very red blocks here, and others are white. The darker it is, the more frequently it gets access during a given program execution, and this is program dependent. So different programs have different maps of the memory access. By observing this access pattern over time, sorry, I'm getting a bit nervous. By observing the access pattern or the heat map, the attacker can actually learn quite a bit of information because it can use the prior information. For example, it sees that this location gets access on a periodic timeline. So maybe at the next T, it'll infer that, okay, this location might be the next location that gets access. So it really, the program can, execution can leak quite a bit of information with the ordinary RAM. This is not good. And so we claim that non-uniform distribution of memory access can leak information. Okay, so what about if we simplify it? We can plot a diagram of the frequency and the addresses. Could be probably not as smooth as this, and it could be like certain locations spike and others remain 0. And we would like to make it uniformly distributed so that this the access location doesn't depend on prior knowledge of it, and it's statistically dependent for each of the access. And ORAM is such a tool. Oblivious RAM is such a tool that does the work. Here I give the definition of ORAM. It's a class of algorithms that preserve user privacy by making these access patterns in memory uniformly distributed or statistically independent from each other. So it hides the true or logical access patterns and prevents information leakage. Or we can express it by this relation, so that for any two program access patterns, P of X and P of Y on inputs X and Y. Inputs X, Y are like sequences of read and writes that users issues. And applying a ORAM layer on top of the RAM can show that they are computationally indistinguishable. I have not introduced the concept yet, but I'll do it in a minute. All right, back to our original example. Yep, we applied the ORAM layer on top of it. So now even with the presence of a powerful attacker with the information of the whole memory and memory access and patterns, the history of access sequence, they won't be able to guess any secrets that's related to the address. So data encryption solves the data problem, and Oblivious RAM solves the address problem. So address over the ORAM mark check. Then naturally, we'd like to ask, how do we construct such ORAM? Here's a trivial construction. What does it look like? So it visits all memory locations and do dummy operations, but only does meaningful operation, for example, read and write to a specific location issued by the user. Well, as you probably have an idea of how expensive it is, and it's O of N complexity, right? So naturally, we'd like to ask, is there a better way to do it? Well, researchers in security community has strived to devise this solution called Path ORAM. And ORAM is, as you indicated by the name, it's somehow related to a tree. So it's a tree-based algorithm, and it's a practical implementation of Path ORAM that has a small client storage. We call it a stash, and we show that it won't exceed the complexity of login, the omega constant. So functional-wise, it simulates the regular RAM. So that means the interface of Path ORAM is the same as the regular RAM, where you do read and write access, and there's some guarantee to it. Security-wise, we showed that Path ORAM makes any two memory access patterns of the same list and computationally indistinguishable. All right, this concept came up a second time. the mechanism. Here, I like to talk about how Path ORAM algorithm works. All right, user integrates this Path ORAM system under the hood, which it is a tree that looks a very simplified tree like this. And each of the node is associated with some number of blocks, which is the unit memory that you do read or write access with. And for each of the entry, it has this pair of block ID. You can think of this as the logical or virtual addresses to the memory and the corresponding data stored in it. Stash is like I mentioned before, it's on the client side. So client can see it, and this is attacker won't be able to see it. And we also have a position map. It's essentially a dictionary that maps all the block IDs to the nodes. I'll give an example. And it's dynamic to maintain the relationship block IDs and nodes. Here's the algorithm. Let me walk you through with the algorithm with a concrete example. So imagine that the user wants to do write operation at address 11 with some new data that I call data n. And what it does here is that imagine first it maps to node 3 somewhere in it. Here we do the uniformly, we randomly assign a new node to this position, or like remap this block to a new node. And this new node is uniformly drawn from a uniform distribution. Sorry. Then we update the position map here from 3 to 4. That's the new node. Then that's where it's supposed to map. Then it should look like that in the next time screenshot of the tree. Here, what it does is that it reads bottom from the root node to leaf node and all of the blocks along this path into the stash. So then if we're doing a write operation, we do the update in the stash. So that's a normal update function with the key being the address here, and you put the new data in. The next, we do the write back because stash is a local client storage. We show that it won't exceed a certain upper bound. Otherwise, the whole tree maps to the stash and it's useless. So here we try to find opportunity to write back to the tree as much as possible. But it has to satisfy certain criteria highlighted at line 11. Yeah, it does the write back to the node. Of course, my animation didn't show that it gets shuffled, but when you write it back, it's not necessarily the same order that it's before it was written into the stash. So we maintain this main invariant that anytime each block is mapped to a uniform random leaf node in the tree, and on stash blocks are always placed somewhere in the package along the path to the map leaf. This is important because we need to use this to show that our stash won't exceed our upper bound. So apparently this is oblivious because here at line 2, every time we do access, it'll be drawn from a uniform distribution. So that makes it statistically independent. Okay, moving on to the properties of it. First, functional correctness. What do we mean by we can prove the functional correctness of Path ORAM? So here we show that Path ORAM client read operation to some address with this access function should return the same data that it most recently written to the same that address. So same example. So the sequence it writes to the tree should be the same it reads back from it. Formally, we have this. So I define it as the axis as a kind of state monad, even though it has more parameters to the value field. So I compose this read and write axis together, and we show that the data we write to it is the same data that we get from the read operation. Moving on to security property. What does it mean to prove Path ORAM is secure? It's like we need to, given any two client access patterns with the same length n, there's negligible probability for the attacker to distinguish them. Here we use y and z to denote like two original access issued by the user with no Path ORAM algorithm applied to it. And so apparently, can we show that these two are computationally indistinguishable? Based on previous introduction, these two cannot hold the relation of computational indistinguishability. However, with the access function applied to the same sequence, we can show they're computationally indistinguishable. And there's math behind. So since they are each time you do access, the new address is drawn from a uniform distribution. So we can use Bayesian rule to calculate the probability of the failure rates, which is since they are statistically independent, so we can use the product of all the probability that to calculate the address. And L here is the height of the tree. M is the length of the access sequence. So formally, we'd like to show that the position map from folding. Okay. So formally, we'd like to show that the Y and Z sequences are related by the computationally indistinguishable relationship, which is defined essentially accords this probability equation. So let's talk about approach. I know this is CoqPL, and you're all excited about Python modeling. So here it is. Yeah, I got many questions from the reviewer why this is, why you started with Python, not Gallina. And so we have several reasons. This interactive Jupyter notebook is really helpful with the fast prototyping, and it really helps us with understanding details. Original implementation of it is super imperative, so that's why I chose the relatively imperative language. And it's on GitHub, so feel free to check it out. Our formalization is a work in progress. There's some challenges to it, and let me expand on it later. But we haven't shown you the data structure we use. So it is a tree with left and right children and two extra fields, the data entry and also the index. So formally, we have a PB tree. It's not a peanut butter tree. It stands for perfect binary tree. We have a normal tree here, but then we also have a predicate to make sure it's a perfect binary tree. We have some, this is the same function that in the pseudo algorithm is called Writeback, and we have two implementations in Python and Gallina. So in Python, it just recurs over the root, and if you find it's the at the same level, you just write to it. Otherwise, you keep going on with the left and right children. Similarly with the Gallina implementation. Slightly different case analysis, but same recursive idea. Lastly, challenges. We have reasoning about complexity. Verification of intentional properties is hard. Yes, you can nod right now. In the abstract, we mentioned 2 ways to prove the security property, but we didn't really mention about the complex reasoning on the stash. That's because we are not super aware of work on this. I talked to Harrison, and the CoqPL project in ACTA is supportive bagel notation reasoning, but it's in ACTA. Sorry. The second one is proof reuse. We hope to reuse existing libraries and frameworks as much as possible, but sometimes we need to close them together. If feasible, what libraries and frameworks should we use to minimize that gluing process? And also, if necessary, we might need to build our own ones, but then we don't want to reinventing the wheels. Then we'd like to ask how to build library and tools that also can later be adopted by other groups in the community and not just specific for this project. So challenge is reasoning about probability. There are many prior works, for example, the lambda Oblivious. It's like encoding the probability reasoning in the type system to prove that Path ORAM is secure. And other prior work on it also showed using Coq to do probability reasoning for crypto libraries. So we'd like to ask, what are the most useful to our verification goal? Last one is about proving higher fidelity implementation. There's a version of it in RTL, and it contains lots of Verilog-dependent optimization. I see some Kami experts in the room. To my understanding, that it's capable of generating RTL, verified RTL, but it doesn't support verification of existing RTL code base. So we'd like to ask, how do we make our verification process capable of higher fidelity implementation? Here's the summary. Path ORAM is this practical implementation that hides the true memory access patterns to preserve user privacy. Our contribution is to formalize Path ORAM in Coq and prove the first functional correctness and second security property of Path ORAM. There's some challenges as we just talked about. But lastly, thank you for your attention.
Questions?
Admittedly, not a question about the theorem proving here, but is it possible that the algorithm that implements the ORAM memory access could also leak information about things in memory? It seemed like the complexity was logarithmic, so presumably it's not always completely happening within registers.
Sorry, I'm processing your question. So you're saying that it's passed, so it's log of n, and this is not the whole complexity, like all of n. So this like reduce the.
Well, so the point of Path ORAM, right, is to obscure memory access patterns.
Yeah.
The algorithm itself presumably also uses memory because it's not a constant time algorithm and can't fit in a finite number of registers for all problem sizes. Is that correct? So it also accesses memory.
Yes. For example, the facilitating objects like the position map is somewhere in memory, that's for sure. And we assume that the attacker can they have access to all these information, and it's still secure. And there's such a powerful assumption. Yeah.
Thank you.
Thanks.
You use computational indistinguishability to say that for two different executions, the attacker can't tell them apart. I'm curious what makes that not also an information theoretic indistinguishability where you literally have the same probability distribution? Is it just that you're using a pseudo-random number generator instead of a true random number generator? Or is there anything else that makes it not information theoretically secure?
Uh, uh, okay, put implementation aside, whether it's true randomness or pseudo randomness, we showed that the core here is that they're statistically independent. So the current access is has nothing to do with prior sequences, accessing sequences. So theoretically, yeah, we just draw it from uniform distribution and do the calculation with the probability. Sorry if
Okay,
I don't know.
maybe I'll take it offline. I didn't
Oh.
fully understand.
I'm happy to take it at lunch if you're available.
Hi, I'm Sky from University of Chicago, and this is really interesting work, and I'm interested in whether or not there are formalizations here for things such as the uniform distribution, because I'm not sure if that's something that has already been done or if that's future work to formalize uniform distribution properties if they're run on client versus server.
Yeah, thank you. Yeah, that's something we've been thinking about it too, right? There are lots of work on cryptography in CoQ. So this is a very basic concept in cryptography. So we assume that some framework has already introduced this or built some primitives in CoQ already. And we hope to adopt if it's already existed. Yeah, but I imagine that for this project, there will be lots of concepts that we still need to build definitions and reasoning facilities ourselves.
Okay, this is a good place to stop and thank the speaker.